Chairs provided to us by Dan Muir and the Hagley Museum. Why, we knew it would look like a sparse crowd because we have so many chairs now. But thank you very much. They'll be very helpful to us as time goes on. I think everyone has been here at least a couple times, and most of you to all the lectures, with the exception of Ann Cleary. Ann is new tonight, so I'd like to introduce her. She's a neighbor who lives right behind us here on Ben's Road, and has a husband and a son. However, she seems to be the mechanical one in the family, and she wants to learn to drive a Stanley and to learn the operation. So she's pretty sharp, so she'll catch up, even though she missed the first 3 lectures. So welcome, Ann, and as you can see, most of our group are men, but we have Roseanne. We've been very happy to have her, and she hasn't missed yet. So that too, the next big hurdle will be getting my wife out here, and I think maybe we can do that one of these days. So Bob Wilhelm, as you know, tonight is going to talk on Stanley boilers and controls, and so this automated system is about to begin here.
Reason for the slide projector and everything is there's only a couple of people in the country that have built Stanley boilers, and I think even less yet that have built condensing boilers. And I'm one of those, having built one for my 735 a couple years ago. And as I was doing that, in fact, as I did the whole restoration, I documented what I was doing, and that was all done with a digital camera. Hence, everything is in the computer. And so a lot of the slides you're going to see tonight are either of some of the cars here taken with a digital camera, or stuff as my restoration went on. So that's why the slight difference in audio-visual stuff. Starting with this drawing, I think Bill passed it out last week. It's all of the plumbing and everything that's involved with a Stanley. And I call tonight's lecture Water and Steam because that's the part of the car we're going to deal with. Starting with water coming out of the water tanks, either located basically inside the car or underneath the car, pumped up to the parafuel pumps. It's then cycled up through. There's a water automatic on some of the later cars. This happens to be a plumbing diagram for a condensing car.
Move the mouse.
Move the mouse.
I didn't realize I had the screensaver on. Sorry.
No, go back.
Okay.
Now you got them all.
Now it won't go page down.
Put the arrow.
I got
Put the arrow on your
Let me
diagram.
turn the screensaver on, sir.
If any of you want to know how to do that, and you're Windows fans, you're about to see it here. Just go into Display Properties, Screensaver, and all the way up the top is None. And apply it. You have to apply it?
Yeah, you got it.
Okay.
Go back to the first one.
Back through the water automatic, which we'll talk about tonight. That puts water in the boiler. Burner last week, underneath that, converts it to steam. The steam then comes off through the throttle, superheater, on back to the engine. The exhaust then comes off. There is a preheater for the water actually coming from the pumps and going into the boiler. It's then set to the condenser or radiator and cycles back in as water to the tank. Again, this is for the condensing cars. So essentially anything that's on this diagram that's in blue, either dark blue for water or light for steam, we're going to be talking about tonight, that loop for the car. The thing that's unique about the steam car when you're riding one and get to drive one is you feel the push of the steam. The steam is pushing on the piston and you've got a constant push for the whole length of that stroke practically. and then that piston is pushed back. It's not like the internal combustion engine where there's an explosion and then that thing just kind of rockets forward. It's an even push, and there's a different feel to the power that's developed because of the steam that's acting on that engine. And if you look at engines in general, the steam engines are the only engine that develop maximum torque at standstill. The thing, crankshaft is not turning, and you've got 600 pounds of steam pressure for some of the later Stanleys on it. You've got 7 tons of force acting on the crank to turn it, and it's not turning yet. So internal combustion engines and all have to be running to develop the torque. The Stanleys develop maximum torque from standstill, and then on as it starts to, the crank starts to rotate and that sort of thing. There are the same number of power strokes in the Stanley for one revolution of that crank as there are for a modern 8-cylinder car engine.
Say that again.
There are the same number of power strokes for a Stanley as there is in an 8-cylinder internal combustion engine.
I thought it was power throughout.
But it's power out and back, so there's 2 power strokes for the piston to make one turn. In other words, for that crank to make one turn, you go through 4 power strokes. Because you're pushing it out and pulling it back,
And 2 cylinders.
and you've got 2 cylinders. Now next, in 2 weeks, Herb will talk about the actual Stanley engine and show you that piston arrangement, how that's all done. But if you look at the internal combustion engine and the 8 cylinders and how they're delivering power through one rotation of the crank, they'll do it in one rotation through all 4 cylinders. Remember, it takes 2 turns to go through all 8 cylinders at one time. So in one turn, you get 4 power strokes, one revolution of the crank. The Stanley's doing that with 2 cylinders. Did I do that backwards again?
Put the arrow on the diagram.
On the diagram, the picture I want. So it's page down to go to the next picture.
Yeah.
Enter.
You can keep on getting there.
I was going to slide projector 101.
Down a little. Different ones that look like surround.
Well, it's not the software I'm even used to, so. Or the computer. So page down goes to the next one, okay.
Can't you just use the arrows up and down?
I was using page up and page down, but I didn't remember which one cycles me. Do I hit page up to go to the next one, or hit page down? It's page down to go to the next slide. That's,
Yeah.
so I would hit
Make
that.
me escape.
The story of making steam starts with water, and to hold the water, it's in a water tank. This is the water tank for one of the non-condensing cars. Originally they were copper, as you can see in the picture. Typically 15 to 45 gallon capacity in the non-condensing cars. Around 25 gallons capacity in the condensing cars. The mountain wagons had much bigger tanks, usually in the order of 50 gallon tanks. They were filled through either a cap in the top of the tank, which you open up, or on the back of the car for some of them, or for the condensing cars through the radiator, through the condenser. There are sight glasses or level gauges, depending on, again, whether it's a non-condenser or condenser, tell you how much level, what your water level is in the tank. If you look at the non-condensing cars, you'll usually see a sight glass somewhere on the exterior of the body telling you how much water is in the tank. The condensing cars have usually a gauge down in the floorboard, and it's a float type gauge turning a needle. Non-condensing tanks are up, or condensing car tanks are up under the body. They're a trapezoidal type design. There's straps that hold them on underneath. There's a drain in the center, but again, copper or galvanized. There's both. This happens to be under the 725 and no 735 that's here, and that's a copper tank. Drain plug down here in the bottom of it. There are ports. There's on the pump box side, which is the far side of this picture. There's a set of tubes that come in and come down almost to the top of this, and if you take that out, there's a strainer that slips up in over that suction tube. So there's strainers inside the tanks that strain stuff. For the condensing cars, the non-condensing cars had strainers in the lines. We'll talk about those when we get back to the piping diagram. These were filled also with injectors or steam siphons. There's not one here on the table. There's one back in the glass case. Essentially, it is a 90-degree fitting with a steam line into it. Hook a hose up to it, to a horse trough or to a creek or what have you, and open up the steam. It'll prime and it'll fill that tank, and pretty rapid rate. Playing with mine just to see how it would work, had a 5-gallon bucket and had the pump hose gone to it full bore, and got the thing. It made all the gurgling noises and everything as it primed up, and I was just cracking it a little bit just to see what it would do as I got it going and this sort of thing, and it was priming pretty good. And I said, well, what's it really going to do? And I just gave the valve a good solid turn, 2 turns, and the water level in the bucket just chunk almost, and it sucked air. So it would definitely overcome the pump. And Tom has said on occasion, so if you ever stop for water and hook up a steam siphon, you suck all the dirt and everything else right out of the house, because the steam siphon's got a lot more power than a lot of the old pumps and wells and stuff like this. So I was impressed with how well and how quick they will actually siphon. The 22 in the back still has its original siphon hose on it. Pulls out the back and you can set to it. Some of the cars, such as the 76, has another tank underneath, and that steam siphon is actually hooked to that tank. So you actually transfer water out of a lower tank back into the main tank to pick up for that. Most of the, I guess, Tom, the rest of them don't have their siphons. They may be there, they're not fully functional. The water gets out of the tanks from the pumps, and this is a picture of the pump box in one of the cars. These 2 pumps being the short stroke water pumps. There's also another set of pumps here, the hand pumps. Bill perhaps talked about one last week for when you prime up the fuel system and all. As far as the pair, it would be this set of pumps here. One of them is for fuel, the other one is for water. And that's so you can hand pump water into the boiler. The pumps is when we start get further back to the back end of the car. These are actually driven off the rear wheels, as is the water pump or the oil, fuel pump and the oil pump. So the car's got to be moving to pump water. And Stanley's thought, well, if you run into the problem of running low on boiler water, you need to be able to pump it in there by hand. So the second pump here was set up as a water pump. None of the water pumps here on these cars work. One of the reasons they don't work is, if you look at the volume that's displaced by that piston, it's not much. And you could spend a day trying to get a little bit of water in the boiler. The other thing I found out in hooking up the pump on mine is if you've got any boiler pressure up above about 400 pounds, it gets almost impossible to move this handle back and forth because you're pumping against boiler pressure too. So to use them, you'd have to have the boiler out of steam. Otherwise, you're going to really work your arm out. And then you're going to pump for a long time because there's not much volume there. Sometimes they're used if you're on a hill climb and this sort of thing. If the pumps aren't pumping enough water, you can have the passenger pump. You'll see that on some of the steam tours to try to aid in what the pumps are normally pumping to help keep the water level up.
Bob, it just might be helpful to say that this view is what is under your feet on a non-condensing car. The floorboards are out, and that's why all the pumps and the piping and all is exposed there. But the pedals are to the left of the picture, and the handbrake is upper center there in the picture.
The pump handle is there. It sticks up through the floorboard. This is the pump box that's in the Model 76, and the auxiliary tank that's underneath the car is actually filled through this spout. So this is an extra pipe in that particular car that you won't find on the rest of them. And these lines going back are the water supply lines and also the steam siphon line to transfer water from the lower tank up.
Bob, I'm not picking up the picture very well. Maybe we ought to turn the lights out on your side.
Just this one
The
goes.
ones with the incandescent lights, Tom. And maybe if you have something to show, you could walk over to the light side so it'll pick it up
Okay.
off the table.
If you,
Yeah. Well, that's a little. Yeah, that's okay. That one on.
that one's okay, Tom. If you look at these pumps, they're kind of short in length as compared to this example pump, which is from the later cars. Stanley had both short stroke pumps and then later longer stroke pumps. And the pumps are 1.25 inch stroke for the 20 horse engines. On your handout you'll see the diameters that they used for the plungers that are in them, the pistons that are in them. The short stroke pumps were always driven from the engine, so they ran at engine speed. They tended to be a little noisier. The long stroke pumps were then ran off the axle in the back. And if you look under the condensing cars, you'll see a rod that actually comes up from a little gearbox hooked to the back axle shaft under the passenger side of the car, coming up to the pump box. And a set of gears there turning a crank. So it gives you a longer stroke for these pumps, and the speed is a lot slower. So there's a lot less noise. The hand pumps don't have check valves in them. There's no check valve mechanism on here. The two cap screws here are the check valves, inlet and discharge. And all they are is small round steel balls that basically move a little bit up and down as the piston moves in and out to suck in water and then discharge it. The
Did it again.
Gotta pay the electric bill.
Or feed the mouse, one or the other.
feed the mouse. I thought you had to apply that, not just okay it. Anyway, just remember. So the check valves here are also used for the hand water pump. The single line there is ported into the back of here. And sometimes there's in fact a valve here. So the hand pump will also use the check valves in one of the two engine pumps, or main pumps. This is a shot straight down of the pump box in a condensing car. The long stroke pump in the rear here. This is under this part of the seat support is where the second pump sits. Here is the line that's coming up to the hand pump, the valve at the end of the pump. So it uses the check valves on the front pump. The oil pump is here for pumping oil for the end, putting into the steam. And then the fuel pump is sitting here in the back. Here is the crank rod coming through the back of the pump box. That's the rear of the car, front of the car. Crank rod in between here to move these move the crosshead back and forth from pumps to operate. Just for reference, this is the pilot fuel tank and the engine steam oil lubrication tank, both under the seat. Telling where the water level is in the boiler, there were a couple of ways that Stanley did it. One way in the early cars is they basically had a cylinder with a little bucket, a little cable and some pulleys and a little indicator. The thing is prone to leaking, was a real nightmare to maintain, and they invented something that we refer to now often as the Ouija tube indicator, or the triple tube, 3-tube indicator. Problem that you're dealing with is you've got water at 600 pounds of pressure and steam at 600 pounds of pressure. The glass indicators that you customarily see on boilers and everything are only rated for pressures less than that. Now you'll see those used on a lot of cars, steam cars, as retrofits, often called dead side indicators. The glasses do hold, but you've got to watch them and make sure the covers are open, because when they break, you've got to be able to shut them off fast, or you're going to run all the water and steam out of the boiler if you're running it all. So you will see those on cars. For the steam tours, where Tom's cars have been there, we've been the only group that is running the cars on the original 3-tube indicators. These things are miracles into themselves. The center tube is what's connected to the top and the bottom of the boiler. So the water level in the boiler and the water level in the center tube should be the same. You'll notice one tube that comes off the bottom here, there's actually a little set screw in the top. This goes down through a copper tube and to a glass that's on the dash of the car. And this is filled with water. And that water in the glass will move up and down to give you a relative indication of how much water is in the boiler. The way that works is the heat that's in the center tube causes the water in this loop to expand and contract. And that expansion and contraction is an indication of the water level as it sits in the boiler. Now the problem with this is this whole thing gets hot and just stays that way. So you get the water kind of wanting to bobble up and down very high on the glass. So the way they compensated for it is they have this loop here, and the water from the pumps is always passing through here. So when the car is running, every bit of water that's pumped always goes through this side and acts to cool it. So you end up with a differential temperature across this and better control on this side, such that as you're driving and the water level goes down, you get more steam up here. That hotter water heats this more and the gauge goes up. These are just backwards operated as to what you'd think. Normally you look at a glass, it's got low water in it, you say, oh, the boiler's low. Well, in the Stanleys, water down in the glass means the boiler's probably pretty full. Water at the top of the glass means you've got very little water in the boiler. So it's just opposite acting. And one of the things that at least I've gotten used to is when you drive a car for a while, you start to recognize when you're driving how the water moves in the glass. As it tends to change states in kind of increments. But when it's sitting in a state and it's ready to go down, you'll see it start to bob a little bit. And then it drops and holds steady. And when it's ready to go back up, it'll bob a little bit and it'll come back up. And it'll bob a little bit and it might come up a little more as you're putting water back into the boiler. And it's watching and knowing how that thing should normally work and getting a feel for how that indicator is telling you where the water level is in the boiler. That tells you whether this center loop is gotten plugged. It's only small 1/4-inch tubing from here down to the underside of the boiler and up at the top. and you can get particles and stuff in there. Hence the blow-off valve on the side that you can open up and blow the crap out. And you'll be driving along and that thing will not be moving. And that's usually an indication that this center line, that loop between the water and the steam, has gotten some crud into it and it's plugged up. And you need to pull over and just blow down the 3-tube indicator a little bit. Blow water and steam through it. Now, in doing that, the other thing that's going to happen is you're going to heat this tube real high, and you can actually run the water out of the indicator because it's open to the atmosphere, the glass tube on the dash. So when you blow this down, you'll see that thing bobble up and down because you've really superheated this.
How long when you pull over, how long do you have to blow it out? What's it take, a minute, 2 minutes?
Oh no, nothing that long. It's usually a quick opening and closing. If it's plugged, usually before you start firing up, I'll open up to make sure it's clear, close it up. A lot of times before I leave, I'll do it. Sometimes you've got to open this a turn or two, and then it'll blow out whatever is in it and blow pretty good and close it. And you can just crack it a little bit and close it. One of the things you also need to watch is, and we'll talk about this valve design, is if you've got dirt in here, crank it down tight again. Now you can score the seat, and now it will weep all the time on you. So it's opening and closing it quick a couple of times, to let it blow out. Okay? So 3-tube indicators. Various versions of these, but that's pretty classic as to what it is. It's a pretty unique little design. Because they're prone to plug up and you've got to kind of really know what they're doing is why folks have put the dead side indicators on them. For the, this is the indicator between the steam gauge and fuel gauges on the 76. Here's the water level. Down at this point, boiler's pretty full. Normally when we're running, wants to run in this area somewhere. Got a little bit of steam space at the top of the boiler. That water level will bounce in here. When it's up in this, gets up into this area, starting to open up the pumps. When it gets even higher, making sure both pumps are running. We'll talk about operation of one pump or two in a little bit. Later on, Stanley's went to what's called the kidney type of water indicator. Example of that is here. This was mounted, this part of it is mounted on the boiler side of the firewall. This is sticking through the firewall so you can see it. This one's missing its glass and its little needle. Essentially what's in here is a float on a shaft. Shaft is coming up through here. The fins are to dissipate heat. There's a magnet in this head that's coupled to the needle that just would be sitting on this gauge, on this pin. And so it's magnetically coupled. So the steam side is always on one under pressure behind this faceplate, if you will. It's brass back in there. And then this part is out in the atmosphere under no pressure. So it's using magnetic coupling back in 1916 to 1917 to make this indication transfer. So this is actually not a Stanley invention, but it was invented and assigned to the Stanley Motor Carriage Company. Again, condenser cars used that one starting in 1917. Water level control was initially done by a valve that's underneath the dash, or underneath the steering column. And normally when the pumps are pumping, when you're running along, the pumps would be pumping because that's a direct mechanical connection. There's no way to stop it. So that water that's being pumped is coming through the 3-tube indicator and cycling right back to the water tank. the valve that's on the bottom of the steering column closes off the discharge going back to the water tank. So now as the pumps are pumping, they're building pressure. There's a check valve in the system, and you build enough, it's in the line that is between the discharge of the pumps and the boiler. So now as the pumps build pressure and build up to 600 pounds, now there's more pressure on the pump than what you've got as steam pressure, lifts the check and forces water into the boiler. So closing a valve on a Stanley starts water flowing to the boiler. Another, just backwards is the way you'd think it should be. That would start either one of two pumps putting water into the boiler, depending on how you have a second valve, which controls whether a second pump is working or not. Remember when I showed you the picture earlier, there were two pumps, both under the floor or in the pump box? One or two pumps can be chosen to put water into the boiler. On the condensing cars, unless they were specially plumbed, you always got two. But on the non-condensing cars, you have one pump or two pumps. And for example, on the 76, you'll see two valves right in front of the seat, right between the driver's legs. The left valve of the two is the second pump valve. So closing that valve starts the second pump operating. It closes the discharge path back to the water tank for that pump, and now forces it to build up pressure and go past the check valve and put water into the boiler. That can be closed all the time, and if the one on the steering wheel is open, they'll still both discharge back to the water tank. And then when you close that, both will pump to the boiler. Or one if you have the second pump valve open. After 1915, the process was automated with something called the water automatic, which is located on the passenger side of the car, right next to the boiler. This happens to be a picture of the underside of my car. This unit is sitting in here. It is mounted at a slight slope. This end is connected to the bottom of the boiler, or the water side of the boiler. This side is connected to the top of the boiler, or the steam side. And what's happening is water coming from the pumps is directed into the back end of this. This is the valve mechanism on this. Water coming from the pumps goes here. This is is piped back to the tank. When this tube has got water in it, it's cool, contracted, and this water that's coming in from the pumps is allowed to pass right back to the tank. But when the water level in the boiler drops sufficiently so that the water level in the boiler is below where this tube is sitting, it gets steam in it, it heats up. As it heats up, it pushes the valve stem into its seat here at the back end of the valve and plugs off the passageway back to the water tank. So now the pumps are building pressure, push the water past the check valve and into the boiler. So the water process with the condensing cars is automated with the water automatic. Now there is another valve on this that you can turn that forces water to the boiler all the time. And essentially overrides this to always put water in the boiler.
This is only on the condensing car.
Only on the condensing cars. Non-condensing cars, you've got to manage water yourself. And manage it by watching the indicator bobbing up and down for the Ouija tube.
And trusting it.
Yes. For the condensing cars, you had a water automatic, and you also had the improvement of the kidney type indicator.
Would it be good to have something like that on the non-condensing car as a backup, or?
I think if you're going to drive a Stanley, you need to know how one of those things work. Just understand the car. To me, I think these things are neat. And once you really understand how they work, and you get the feel of this particular car does, the way that water indicator works and this sort of thing. I mean, to me, I don't even think about it anymore. It's something, as you're driving a Stanley, you need to learn to start looking at all the things. You've got to be watching that the winker is putting engine oil in, that you've got good boiler water, where your steam pressure is. There's a whole bunch of things that you're starting to have to monitor anyway. To me, watching how that water gauge is popping up and down is just another one of them. And it doesn't take but a mile or so before I know whether this thing's got a problem or not. Just knowing how that car works. Now, to drive one of the other cars, for me, this would be the first thing I'd be real leery of, because I don't know how it wants to respond. So I'd want somebody with me that knows how that car works water-wise, because the last thing I want to do is scorch the boiler.
Gene, a lot of people have put those automatic bypasses or automatic regulators on non-condensing cars. One thing is there's not much room under the hood to get it in, but it's possible to do it. But I kind of agree with Bob that the more things like that you rely on, the more you tend to take your mind off what you should be thinking about. And, I don't like them on non-condensers. But I have to admit they usually work pretty well on the later cars.
It's maintaining it, knowing that you know, before you fire it up in the morning, make sure there's water running out of it. One of the things that can really mess you up is the gauge on the dash. I always look at where that water level is before I fire up because it's cold. And from that I know how far it will move up. And if somebody's added water to that, so now it's sitting, instead of up normally an inch, it's up 2 inches. That means on my gauges everything's going to be, I'm not going to be sitting in the center of the gauge necessarily, I'm going to be reading high. So it's knowing where that thing even starts in the morning, because the water isn't going to change. So it means it's just going to be reading naturally higher, which would tell you initially, oh, I'm lower on water, keep adding water.
Well, then would we have to add water to that gauge if you run the car more often to keep it at a certain level? I mean,
You do have to replenish it. I mean, it is a small open area, and it will lose it to evaporation. If you blow the gauge down really hard and really get that tube hot, it can boil out the top and run over. And now the gauge is running low for what's actually in the boiler. But it's kind of, again, it's kind of knowing the car and getting the feel of the car.
Thank you.
If you're driving one of the non-condensing cars and you lose the water prime for any reason, one of the things that you'll hear is those pumps pumping, and they'll change. In fact, when you open to bypass, they'll get quieter because they're not pushing against pressure. So there's a little bit of mechanical slop in that linkage and all. You'll hear them making a little bit of noise. When you open the valve underneath the steering wheel, so now that you're just recycling the water, they're not building pressure, a lot of mechanical noise goes away, so the pumps change. So if you're driving along and you know you've got the valve closed and you're trying to fill the boiler and the pumps get real quiet, they're not pumping anything. One quick way on the non-condensing cars to prime them is simply open up the bypass. Open up the valve under the steering wheel and let them try to reprime and push the air back to the tank and pick their prime back up again. And usually you can drive a short distance and get those to pick up. The condensing cars with this, the only way I've ever been able to prime them is to jack up the back wheel and break the line. Because if this gets hot, it shuts the return route back to the tank off. So if you've got air in this thing, it sits there and just acts as a spring, and the pump won't pick its prime back up. You've got to break the tubing connection. In fact, that's a valve I want to add on my car, is a way to bypass this so I don't have to keep taking this apart all the time. I've lost prime once, and I lost it because the check valve was actually letting steam get back in and warm the pumps up. Hopefully that's been corrected, but it was such a mess to get this thing apart and get it primed. I'd like to have the valve to be able to do it just a little faster. The exhaust steam coming back from the engine comes up into basically it's a tube about that big in diameter. They vary depending on the cars. That's got the water circulated through it. When you close the valve under the steering wheel to start forcing water into the boiler, it actually forces it through the heater and then into the boiler. So it's using the exhaust steam to try to preheat the water a little bit going into the boiler. This was an addition to the cars made after 1912. The earlier cars don't have this. And it was continued through until the end of production. In the non-condensers, these were often located in the exhaust for the going out the back of the car. So you had the exhaust gases as well as steam exhaust all going out, trying to help heat the water going in. In the condensing cars, as it was a closed loop, the exhaust basically just came out right in front of the firewall underneath the bottom of the car, and it was just the steam that was circulated through the heater. The water that is brought back off of that heater comes through, and this is the boiler check valve. That is nothing more than a casting with a ball bearing in it on the seat. The water coming in lifts the ball, blows past the ball, goes into the boiler. Boiler pressure pushes down on the ball to keep it seated. A lot of times if this isn't sealing, you'll get steam working its way back through all this tubing, working its way back into the pumps and losing the prime. In fact, this is also the check that you'll find right after the pumps. As to what another, they'll usually have one at the discharge, to feed water into the feed water heater. So there's actually, for that boiler loop, would be 2 of these. And you'll see these also in the fuel lines and some things like that. The key to making steam is with the Stanley boiler. It is fire tube boiler, which means the flue gases come up through the tubes of the boiler. This is a shell of a boiler. These were made in various sizes. Your notes show you anywhere from 14 inches all the way up to 26-inch diameters, depending on the size of the engine, the year of the car. 23-inch diameter was a very common diameter, and that happens to be what this one is. Basically, it's 2 drilled out flue sheets. This one is having the one sheet was already welded on. Solid rods to line all the holes. Will top the other flue sheets being welded onto the boiler. It's welded all the way around the end. Now the earlier Stanleys, this was pressed. This was the bottom and the sides were all one piece, and then the top flue sheet was pressed into it. And then there's a set of steel bands, top and bottom, holding it in to give it strength. Also giving them ways to set it into the frame and grab a hold of it, hold it into the frame.
Is this just cold steel or is it?
This one's boiler steel. the non-condensing Stanleys have started out with copper boilers and then went to steel shells with copper tubes. The brass plugs here around the side will be where blowdowns will be located, where water fills will be located. On the top side, the center hole will be drilled for the, actually this is the top. Center hole will be drilled right here for the steam to come out. The bottom doesn't have a hole in it. This is hydraulic tubing, 1/2 inch diameter. The Stanleys originally used, what was it, 31/64, Tom? 33/64 OD tubing on theirs. Why the size, I don't know. This is 1/2 inch hydraulic tubing, steel. It's got the size. They're then put through the boiler. This particular one has 636 tubes in it, which is less than a Stanley boiler. My spacings are just a little bit further apart than what Stanley used. Once they're all put through, the bottom sides get welded. On the copper ones, they get spread with either one of the drift punches driven in the bottom to spread them, and if they're copper as well, to give them strength, there's a little ferrule, steel ferrule, that's dropped in first, and then the ferrule is expanded as well as the copper tube inside the flue hole. The way that the ones here were expanded, you can buy small little rolling expanders. This sits in the drill. The center shaft that's moving is tapered, and there's little long rollers here, and this thing just turns and just rolls it bigger and rolls it out to a larger diameter.
Like forming the lip of a tin can.
Basically. The punch way is noisy. There's nothing wrong with it. I preferred to do it this way with the steel ones. In an air drill, I could control it. I could roll them real pretty uniform.
And that roll is the water seal.
It is the water seal. On the bottom, though, it also then gets welded. On the top, it is only rolled. Now, one of the things Tom had told me when I was making this is cut your tubes as you need them. Well, because I was cutting them elsewhere and had automated cutting equipment, I cut all the tubes the same time, same length. And the length was fine on the outside. But after the welding process, I got a concave top and bottom on the flues. And that caused the flues here in the center to be a little longer, sticking out than they should have been. So it forced me to have to use a tool, this one, which is a mill and a guide, to go down over the tool, over the tube, essentially, in each hole, to mill it down, and I could adjust this for the height, so I could get all the heights uniform. So I had the extra step in when I built this one of having to knock some of these down here in the center 3/8 of an inch, because they were that much too long, because of the belly that got into the boiler. Once that was done, then I rolled them all. Stanley boilers get their strength with piano wire. 300,000 pound tensile strength piano wire. And there's a set of pins put in this steel ring, and they're wrapped. And there's about 25 pounds of tension on them as they're done. The way I did this one was I have a small variable speed AC gear motor, a little variac. I can control the speed. My brother's forklift just sits here on made a set of plates, all thread to go through the flues. Motor sits here on the end and just rotates this thing. The wire's coming off a spool and two pieces of metal together with a clamp to give me the tension I need. And all I do was basically standing here and keeping the wire layer by layer all the way through.
One gauge used throughout.
One gauge used throughout, 3 pieces of wire, because each layer is its own independent piece.
You didn't do a continuous?
Well, it's continuous once here's the pin. I put one layer on all the way across and terminate it. Then start again
With a different pin.
with a different pin and go across and pin it out.
Otherwise, you're cross-threading. If you try to go over and back.
In fact, that's why this is close, because it was real easy to get this thing to want to not lay like my fingers are, but to start picking up spaces. And I'd have to stop it real quick and usually just could push it back over and line it back up again. And this wire doesn't bend. Once you get the end of it, holding the tension, you've got to heat it cherry red to get it soft enough. You can get it on the pin and get it wrapped.
How many layers was on there?
3.
3.
This one was drilled 636 half-inch holes on a CNC machine. Here's the 2 boiler plates when they were still square. I did the layout on the computer at home, took the floppy disk to a friend of mine's got this mill. He fed it into the computer. It creates the program that actually goes through and drilling it. All he did was set the feed rates for the holes. And my drawing was for half the boiler. And once it did half of it, release the clamps, turn it around, re-register it real quick, and start drilling the other half. 20 hours of drilling. And then the same drawing then had the circular for milling that out, and then he changed the tool to put a bevel on it for welding.
How many drill bits did you use?
2. Which surprised me because I bought a dozen. I figured we were going to go through drill bits.
Were they
Anyway.
carbide or drills, or just regular steel drills?
The good quality ones from MSC, cobalt,
Cobalt.
pair of cobalt bits.
Cobalt coated.
Hmm?
Cobalt steel.
Well, cobalt coated or something.
yeah,
It's
coated.
kind of a gold color.
Yeah.
Yeah. But Tony said to me, it's all in, metalworking is all speed and feed.
Yeah.
And he programmed the machine, it just kind of poked through. It would pull off a spiral about that long, back up and then go again. And just all the way on down, and then index over and just go again. So the nice thing about it was, once you set it, you walk away from it.
Set it and forget.
Just another picture of it before it's got the wire and all on it. This is set up to drill the holes here in the corners and everything. I had set the boiler in the car and marked where the steam lines and everything needed to match up. And then magnetic base drill to drill it.
Your car did not have a boiler, right?
It had a boiler. It was retubed in '88. And when I started to do the pressure test on it in August of '97, I got to 250 pounds, and there was, you've seen these blue Danish metal cookie cans? There was one of them sitting on top of it, and the thing took off. Water squirting right out. I mean, most of the time it runs down. This one was right near the top and angled up, and it just, and another one was starting to drip. Not a problem. Put a pair of boiler plugs in it. Got it up to like 325 pounds and took out another one. Plugged that one. Got it to about 400 pounds and took out 2 more, and I said, that's it. That boiler was also 14 inches high, car came with 18-inch high, and this one's 16. Yeah.
Would there be any advantage of painting the boiler shell with the heat-resistant paint before you wrap it, if it's an older boiler that may have some, like rust on it, or?
There
keep it from
is
rusting?
a boiler paint that I found out about from Steve Jensen
Yeah, we use it.
that they paint the steam locomotives on the Wilmington Western with. And absolutely, Steve says, when you look inside that boiler, it looks, you know, just like it was just painted. So this one had a gallon of that dumped in it. It was put back on the fork truck and spun to slosh it all around, try to get all the tubes,
Inside.
all that sort of stuff. And then I took a plug back out and let it sit and drain. And then I put a couple of fish tank aerators on it just to blow air through it for a couple of weeks.
So you did something similar to what people do in gas tanks by putting like a sealer to coat the
Well, I
inside.
used the steam locomotive sealer.
Mhm.
One of the things that I was told when I talked to the company about it is it actually improves the heat transferability of the boiler. And to see if that was true, I took 2 soup cans, put the same amount of water in both of them. One of them I had painted with this paint and set them on. Well, it does, but it's only like by putting them on the same electric burner and letting them heat up. The one with the paint ended up getting, in the same period of time, it got to boiling. By the time it got to boiling temperature, the other one was still had 5 degrees to go. So there is some slight improvement. Whether or not you'd ever notice it in this thing, on that controlled tester was.
You would need something very clean in order to paint that first, otherwise it would.
Yeah, well that
And here's the
shell
guy.
was cleaned and everything before all the tubes went in. The tubes were all cleaned. And then that's when I put the stuff in it. In fact, it was done at this state before I had the wire on it.
Could you use that paint on the copper tube boiler too?
That I don't know. That I don't know. And then the outside I did paint with an engine black before I put the wire on it. High temperature engine black.
Question.
Yes.
The tubes, now, you say you welded the tubes to the bottom.
Yes.
Flue plate, did you call
Flue
that?
sheet.
Flue sheet. Then at the top, the tubes are just bent over.
They're actually rolled with this to expand them into the hole.
So in essence, you're drawing that tube from end to end to draw to put pressure on that roll to seal.
This goes in and rotates and spreads it. So it spreads it in the hole. The thing you've got to watch with this is you can actually, on the boiler, when you're doing it, you can cause the holes right around it to deform. So when
Through the flue sheet.
by deforming the actual flue sheet itself. Okay?
But anyway, that's what's withholding 600 psi.
Yes,
Just that rolled over.
just that roll too.
600.
Now the structural integrity of the boiler is all the piano wire on the outside and all the tubes on the 2 end plates.
There's theoretically, if you plugged all the tubes, your piano wire is going to hold it to keep it from.
Usually what you end up if you overpressurize a Stanley boiler is you crush a tube and it starts blowing out the flue sheet or blowing through the tubes.
So it blows in instead of out.
Yeah.
Collapses.
Of course, sometimes it just collapses and you blow anyway, if the tube just flattens. Copper tubes will do that.
Flatten but won't release the pressure.
Did they use copper tubes to withstand those?
This is a copper tube boiler with the furrows in it. This is an older boiler and it's got furrows on both top and bottom. The original boilers were made
It's
that way.
welded on the bottom.
It's wedged on the bottom with a furrow. The problem with the condensing cars is coming back in the exhaust steam is the spent oil. And that oil can settle on the bottom and create hot spots. And those hot spots then cause different rates of expansion, and you can get leaking on the bottom flues. That's why they welded them. And then at that point had to go to steel tubes.
Would it be arc weld or MIG weld or?
Originally gas welded. These were TIG welded. The ones I just did. Or I had done, I didn't do the weld.
Good. Were they magnafluxed or checked or anything like that for?
I don't know if I've got it in this group. I pressure tested that boiler to 1,200 pounds and it held it for 10 minutes. I figure that's close enough. I'd read somewhere that Stanley's used to do their originals to about 1,000. So I figured the steel in that one is actually heavier than what they use. Sidewalls a quarter, 3/8 for the flue plates.
Copper tube boilers, I think they probably tested at about 800 pounds, 750, 800, because they didn't want to collapse a lot of tubes, and the copper was not as strong as the steel, but the transfer of heat was better. And so when they went to steel tubes, they didn't steam quite as well.
Did they ever put fins or anything on the tubes? to
Well,
try to improve
I don't know how you get them in there. 'Cause you know, they have to be on the inside. If you put anything down it, you're going to restrict how much is flowing out of it. Gas
They
is not.
believed in those days that heating surface was what counted, and that's why they had so many small tubes to get more heating surface. And a 20-horse boiler like Bob has been showing here had a little over 100 square feet of heating surface, 105 on it, Bob,
Something like that, yeah.
And that's a lot of heating surface for a little boiler 23 inches in diameter. And of course, they also were very much concerned about weight, and that's why the shell is so thin, and they used the piano wire to make them safe. And in case you wonder, well, it was really 500 or 600 pounds safe. The racing car in Florida in 1907, they carried 1,300 pounds, and we know it wasn't safe, but they got away with it.
With copper tubes.
With copper tubes.
We think copper tubes. Yeah, I think so.
Is there any consideration that of different thermal expansion rates, especially with the copper tubes working in steel flue sheets? Would that be a concern if they were?
I don't know that you've got enough length to change it. You know, the short height. They're going to slide at the top anyway. If they have to move, because I mean it's still. This one initially weaked a little bit. It held its 1,200 and it dropped back to like 1,100 in 10 minutes. But it was weeping around some of the tube holes at the top, and it took about 4 firings before the rust sealed it up completely.
They
Then it
used to
doesn't
say
move,
just a little weeping would take up, but if you had a squirt, then you had to fix it. That was sort of the old Boilermaker's rule of thumb.
That's where having Tom's experience, because I'd seen it weep and said, oh, you know, this I gotta keep rolling or doing something. Tom says it'll rust up. It'll rust up. It rusted up. It's tight.
But once it rusts up, then the tube can't move with respect to the sheet. Is that correct? It's more or less like it was welded?
I would imagine it's in there, but I think you probably they're awful hard to get out. But they will come out.
Well, I'm trying to get to why you weld one in and not the other.
You weld the bottom ones because when you get the oil and all from the sediment, you get different rates of expansion, and it causes the openings to open up because of the heat differences, and then it starts to want to leak. So the welding absolutely positively stops that.
Why wouldn't you weld the top too?
I'm not an engineer, but I think the reason in the old days was that if they did get excessive pressure in the boiler, which could happen by hydrostatic pressure if you had the boiler loaded with water, or it could happen with a dry boiler. You run it out of steam and you don't know what pressure's in there. The top head could relieve itself, whereas if they were welded both top and bottom, I think they thought a boiler could blow up. Now, whether there was much to that, I don't know, but that was the theory behind not welding the top head.
We installed, for those that were here Thursday night, we were doing the hydrostat. Here's a hand pump, pumping up pressure. There's 500 pounds of pressure sitting on that gauge. Now that one that's the in-cart check. I also did one before the boiler ever got put in. This is checking everything, throttle, the whole plumbing system. This has the steam automatic on it here in the back. The steam gauge is also hooked to it, so you don't want to test it above the pressure of the gauge because you want to wreck that, you don't get the diaphragms and everything.
Those of you who were here last Thursday witnessed the hydrostatic on the boiler up above, and we only went